Welcome, Hornets. We're going to be talking about finding limits that are two-sided. Now, a limit that is two-sided is not going to show a symbol behind the number. Now, you'll notice here, trying to find the limit as x approaches 1. Now, as we saw with a one-sided limit, there was a plus or a minus behind it. But in this situation, there isn't. So if I'm looking for a two-sided limit for some function f of x, then what I want to do is I want to know if I approach from the left or approach from the right, will I get the exact same answer? Now, in equations such as, let's say, a line, that's going to happen very easily. Here we have an example where we're approaching 1, and this equation is going to be y equals 2x plus 3. Notice that my y value will be my limit when I plug in the 1. I plug in the 1, my answer comes out as 5, and you'll notice this is the y value of the point. If, coming in from the left and the right, we approach the exact same point, then the limit is said to exist, and that limit is the y value. Now, this is referred to as the finger test. Moving your fingers along the graph of our line or curve. If, when they meet at the point, then the y value of that point is going to be our limit. Now, it doesn't matter whether the point exists or not. For example, here's a situation that confuses some people. The limit is approaching 5, but the value is defined up here at 7. Notice this is the point 1, 7, but the hole is at 5. The point 1, 7 is a trick. They're trying to trick you. It is only the journey that we are looking at. What value are we approaching when our fingers meet? Don't look at the point above. Look across from the point. This limit is 5, and something to be aware of. So whether the hole is filled in or whether it's a hole, you're still approaching it from two sides. Notice this is what we call a two-sided limit. Here's another example of a two-sided limit. If you wish, you can graph them, but it's pretty obvious. If you have a line or a curve that does not have an asymptote in it, you can plug in your value and find your two-sided limit quickly. But every so often, a situation arises that isn't as pleasant. For example, let's take a look at a limit such as this. The limit as x approaches 1 for 5 minus x over x minus 1. Notice we get 4 over 0. This is bad. Whenever you get a 0 in the denominator all by itself, and there's something other than 0 in the numerator, that tells you that this limit does not exist. You have an asymptote, and therefore you're either approaching the same infinity on both sides, either moving toward positive infinity or both moving toward negative infinity, or they're going in opposite directions. So that means that the two-sided limit does not exist. But that's not the case when we're talking about the limit as x approaches a value from the left or the right. Notice this problem. Approaching a value from the left. Now, I recommend you think about a table of values. Let's go ahead and start by plugging in -2, for example. If you plug in a -2, you'll notice our value is going to be 7 on the top, and we're going to have a -3 on the bottom. Then we go ahead and we'll plug in -1. -1 is giving me a 6 on top and a -2 on the bottom. Notice this is approximately negative 2 1/3, followed by -2. This value is growing. Let's continue. Let's do one more. When we plug in a 0, we get -5. Let's just check it again. 0 gives me 5 over -1, and we get a -5. So you'll notice and this is -3, excuse me, -5. And so this value is growing toward the negative. I suppose I should say it's decreasing. Okay? And as it's going down, we now know that this answer is -infinity. Now, the only way I got that was by using a table of values and looking at what happened. That's what you have to do. Okay? Now, when you get a specific result, such as a 0/0, let's just take a look at one. Let's take a look at the limit as x approaches 3 for x squared minus 9 over x plus 3. Let's do x minus 3. Now, this is a rational function. We've seen these before. When we plug it in, you'll notice we get 0/0, and this tells me that I have more work to do. There's a factor in there that's causing a problem. That factor is a hole. If I factor the numerator to find what's happening, you'll notice the factor becomes very apparent. It's the x minus 3. If I remove the x minus 3, I can find out the location of the hole, which is also the limit. By redoing this and plugging in the 3, I find the limit is 6. So 0/0 is a very important process for us and something that we want to be very careful about. Now, there are a couple of others that we're going to watch out for. For example, the fraction over a fraction. Now, we've seen this before, and there are many to work with. But the idea here is that if I have a fraction that's a composite fraction, I'm going to want to take whatever that fraction is within, and I'm going to want to divide by whatever the denominator is. In this case, the fraction that's complex is in the denominator, and so it goes behind. If we had this reciprocated so that the complex fraction was on top, I'd simply divide by x. Now, my goal is to get the common denominator. In order to get the common denominator, I want to look at the one I have and make an equivalent form of 1 out of it. I distribute the -1. I add my like terms. I use my division rule that says when you have a division followed by a fraction, you take the reciprocal of the fraction and multiply. I now can see that I have x times x minus x plus 1 over -x. The x is reduced, and I'm left with -1 times 1 plus x. I can now evaluate it. Beware, I get 0. Now, there are other types. For example, what if I'm approaching a radical? Here's an example of something I don't like. When I'm looking at this radical, I get 0/0 again. Now, the previous problem didn't give me 0/0. However, if I approached 0, it would have. So here's an example where I would get 0/0. And I follow my examples the same way. I ask, take the numerator. I'm dividing by x, which is multiplying by the reciprocal. I'm getting my common denominator. I'm multiplying by x, and I simplify. And right at the end, when I plug in the 0, I get 3 times 3 is 9. Notice, get rid of the fraction. The radical with the square root is a little bit trickier. Here, I have to kind of work to find where that factor is. So what I do is I multiply by the conjugate pair of the radical term. Since the denominator has the radical term, that's what I use for the conjugate pair. When I multiply, I only multiply the conjugate pair because it's easy to find. Don't multiply the numerator with the other radical. You'll just cause more work for yourself. Once this simplifies, the x minus 3's cancel, and I can plug in the 3, leaving me with an answer of 2. So here you're looking at the 3 major situations, plus what do we do when we hit an asymptote. So if we hit an asymptote, we get a 0 in the denominator. The limit doesn't exist, but I can find either side. And either side will go to positive or negative infinity, but the two-sided limit won't exist. Or I could approach a hole. So instead of an asymptote, I'm approaching a hole. Well, if I approach a hole, I get 0 over 0, and I have to do one of 3 things. Find the common factor by factoring it, multiplying by the conjugate pair with a radical, or by cleaning up a fraction. Oftentimes, when I have the composite fractions like we saw with the limit as x approached 1, I need to clean it up so that I can plug in my value and find my limit. Things are in the way. Things can cause problems. Alrighty, please do the problems that I have provided you that are following this video, and you'll be all set. We will continue with limits and special limits next week. So take care, be well, be safe, and have a very good night. Thank you.